Οπότε για την επόμενη παρουσίαση να ζητήσω τον Αντώνη να ανέβει στη σκηνή. Ο Αντώνης Chariton θα μας μιλήσει για ένα περίεργο κυνήγι που κάνει.
Ευχαριστώ. Thank you. So we'll go from the previous presentation where BGP works without any problem to one where BGP has many problems. But before that, I have some announcements. I have two networks here, Information Society, Κοινωνία της Πληροφορίας, and Sky Telecom. If anyone is here, RIPE sends some probes for you. And if you can host them in your network, come and find me. And I can give you these probes and then help you with setting them up. And the other thing they gave me is 2 t-shirts and 2 polos at these sizes. So if anyone wants this, I got them here from Prague, and I can give them to you. They're available right here. So again, come find me. So let's move on to the main content for now. And we're going to talk about stack routes, or BGP Zombies, as they're called. And to better understand what these are, let's look at this example here. We have 3 autonomous systems, and they are connected somehow, like in the internet. And if you have a new prefix, let's say this one, and you want everyone else to know about it and send you traffic, then what you do is you create a BGP update message with the subtype, like it's an announcement. And then you send it to every other AS that you are connected to, and eventually everyone gets the message and they know how to send traffic to you. And if a link is down or this prefix is no longer used, what you do is you generate a withdrawal, which has the prefix and less information than the announcement, and then you send it over to everyone that you know, and then they send it to everyone that they know. However, sometimes these messages get lost, and this is a problem, because right now we have the 2 ASs that receive the message that say, okay, this route does not exist, everything is fine. But because the last AS did not get that message, then they still think that there is a route and they're going to send traffic to their neighbor. And if this AS has downstream ASs, it's going to propagate that even further, and then they're going to get infected by these zombies as well. So why is this a problem? Well, the primary thing is that, routers are supposed to route traffic. That's their only job. And if they don't do it correctly, if they don't send the packets to the right destination, this is a problem. But you can create routing loops, you can drop traffic, and there are also all sorts of effects. For example, you have a DDoS mitigation provider that you have like 24 hours a month, that's what you pay for. And if you exceed that, then you have to pay basically a lot of money for additional hours of DDoS mitigation. If this route is stuck somewhere and you still receive traffic through that DDoS provider, then they're still charging you for that, and it's going to get expensive. And then, of course, you may get false alerts, you may have, you sold some IP addresses, but 0.1% of your traffic is still going to the previous owner. You have no idea what it is, like everything looks perfect on your tools, there's no packet loss, yet somehow this traffic is not going to you, it's going to someone else. So this is a problem if your prefixes are stuck in someone else's routes, but it's also a problem if someone else's prefixes are stuck in your routers or your upstream, and they infect you with that as well. There are 2 separate kinds of problems. And we know that this can happen with withdrawals, like a prefix or a path or something is no longer available. The thing is, they can also happen with announcements. But this is way more difficult to study, and there hasn't been a lot of research into that. So you have so many problems as operators, and we wanted to figure out if this is a big enough problem. Like, should you care about it, or should you worry about PNIs with Vodafone? And in order to study that, we looked at the literature, and there is a paper from 2019 on this work where they try to study this. And what they do is they use the RIPE prefixes, the RIPE beacons, where basically at midnight every day, there's a certain set of prefixes that are being announced. And then at 2 a.m. they're being withdrawn. At 4 a.m. they're announced again, and it repeats every 2 hours. So what the researchers did was go and check the RIPE looking glass, and out of all the announcements and the withdrawals that you can see here, they basically looked at around an hour and a half after the withdrawal, and they saw who sees these prefixes. Because they have been withdrawn, it should have been nobody sees them anymore. But they discovered that this does not exactly match reality. And they found thousands of times where this happened with the RIPE prefixes alone. And they did some analysis on the data based on address family, and we can see here that, you know, depending on the period, IPv4, IPv6, it could be worse, it could be better. It doesn't really matter that much. So what we did was replicate the study. We did not have a time machine to query the looking glass like many years ago. So we looked at the MRT dumps that RIPE makes available for use. And we found very similar numbers with them. And sometimes it actually got worse. Like the 384, it became 705. So this is actually worse than they initially discovered. And then we looked into the methodology again, like we tried to figure out if something was stuck, you know, 2 hours ago or something was stuck a week ago, to try to get an idea of whether this is like something time related or this is something long living. But we could not really understand that well enough. We felt like we could do something better. Because we found, for example, that 90 to 95% of the time, the paths that get stuck are not the best paths. Which means that if this happens to your prefixes, almost certainly you're using a suboptimal path. So it's bad enough, it happens a lot of the time, but we don't know how to fix it, we don't know what to do about it. So we have to look further into that. And here are some additional statistics here, like only 19% of the RIPE prefixes were not affected. Basically, 81% were affected by stuck routes at some point. So we tried to improve the methodology here because we know that this works, but we want to know how long these routes are stuck for, which specific equipment has problems. We wanted to dive deeper into that because we also want to provide solutions. We don't just want to study this academically and call it a day. We have to eventually, you know, do something about it. So the first thing that we needed to change was that we only have 2 hours where these prefixes are not visible. And in these 2 hours, we discovered that, you know, some prefixes stay for the entire duration. But do they stay for a day? Do they stay for a week? What happens? So we wanted to increase this time frame, but this RIPE service has been running for years. We could not really change it, and we had to do something else. So we created the BGP clock, and what this is instead of NTP and all of these useless protocols, you get the time with BGP. We advertise the prefix containing the time in it, like the hours and the minutes, every 15 minutes, so we don't, you know, take down the internet or some BGP sessions. And so at midnight you have 0000 and so on. And this is UTC. So if you want to figure out what the time is, just, you know, do a trace route or something and you'll know. But then, like, this repeats every 24 hours. We did a minor change. We added the day there as well to repeat every roughly 2 weeks. And we issued, of course, a ROA because this, like, has to be RPKI valid. I used my personal AS for sending out these advertisements. and everything was fine. It was ready to go. And we improved several things. Like right now, these prefixes repeat, like they have a longer period where we can study which routes get stuck and for how long. And we also had better connectivity through my personal network that has, like at the time it had over 1,700 direct unique BGP neighbors. So we could really broadcast that to the internet very efficiently. And we also have more prefixes. Instead of trying once every 4 hours, we try once every 15 minutes. So if there is some chance involved, like if it happens 1% of the time, by rolling the dice so like way more often, you're going to get that to happen more frequently, and hopefully you're going to see more interesting cases. So here are some examples of that. We have the free SAS, like it's a French network with over 200 ASs in their cone, where this particular prefix got stuck. And all of their downstream BGP feeds reported this route getting stuck there. And to help you understand how that looks like, I have this diagram here. You can see basically the origin, which is on your right, and you can see the prefix moving all the way to the ASs that provide the BGP feed to RIPE. If we don't have a BGP feed from someone, we don't know. Like they're also infected. Like we guess all of the 200 downstreams were infected, but only 6 of them had a BGP feed, so we cannot verify the others. We're fairly certain, however. And it looks like this palm tree with, you know, a very long trunk and then suddenly branches off. And in the red box, of course, you can see who we think is the problem, like the AS of free. And we consider the problem to be there because if it happened further down, like it's impossible for all of their BGP collectors to get the route stuck at the exact same time. This is unlikely. And if it happened before in Open Transit here, for example, then it would also affect other downstreams of Open Transit. It would not only affect free in this case. So that's how we can kind of arrive at some sort of attribution, try to figure out which AS this happened in. Another interesting case was Core Backbone, which is a very large AS in Germany, over 2,000 downstreams from what we can see. And we guess all 2,000 of these ASs had this route stuck, but we cannot verify only 21 of them had public BGP feeds from. And this is where it's useful for you to publish your BGP data. So we can know, basically, we can study these events, these internet scale events better. And another one, it's WIT, or formerly MyLock. Another 200 ASs here, they also got affected a lot by that. These are different prefixes. So then, like, we ran this experiment for less than a month. It was an internship project, like we had a summer intern, Iliana, do this. And we had to start, you know, wrapping this up because the internship was about to finish. So we stopped the advertisements. We didn't leave them there generating updates for no reason. And I went and I deleted the ROAS just because they were no longer needed. And then at that night, I received an email from RIPE. And you cannot read that. But basically, if there is an RPKI invalid that they detect, they send you an email and they tell you, you know, either someone is hijacking your IPs or something changed and you did not update your ROAS. So go figure that out. And I said, okay, like probably something is stuck somewhere, I don't know. But I kept receiving this email for a long time. So I kept getting this email every night for 3.5 months. And basically that means that somewhere a route was stuck for a very long time. And when I deleted the ROA, it turned invalid because there was no covering prefix. And then they started, you know, firing alerts about it. So if you want to bypass ROV, that's how you do it. You get the route stuck somewhere, and then you change your ROAS. And now it's invalid, and you see who keeps it and who doesn't. So a little tip there. And it's been 5 months, and I updated here the slide with the current situation. One of these routes, since June or July, is still stuck in the BGP tools collectors. One of them is in Hurricane Electric's BGP toolkit, and recently we have no prefixes stuck in RIPRIS. And these have been invalid for 4 to 5 months. So these networks should have dropped them many months ago from the routing tables, but they're still there. Like, some people can still see them. So we discovered that if a route gets stuck, there's basically no time frame. It can be there for months, or it can be there for a year. We don't know yet. We're still trying to bet on when these routes are going away. And so what did we learn? Like, that's fun and it's nice, but was it useful? And in order to understand one of the things that we faced first is this diagram here. You can see over time how many prefixes are stuck. And we have 2 lines here, and the real one is the bottom one. But what about the first one? Basically, we had some peers where 10% of the routes were getting stuck there. So out of every 10 withdrawals, we're getting stuck into this peers. And this was very noisy. We could not study this effect very well. And these are the peers, by the way. And it's 9.9%, not 10%, but yeah, you get the idea. And the other thing we noticed is that after some time, the amount of stuck routes started going up. And they're supposed to only go down. Like, eventually people, like, something happens, a link, a configuration is applied, whatever it is, they get cleared away. But not only did they not get cleared away, they started, going up without us doing anything. And we looked further into that. It turns out it was Telstra Global, and they have over 5,000 downstreams. And we don't know what happened. Like, we tried to investigate, we were not sure, because we can only see which AS this happened in. We don't know much more, like which router. And basically we assume that something happened, like maybe, a link went down and up again, or a filter was reapplied. And then Telstra started generating these announcements. Because if you send a full table to someone, you send all of your routes, including the stuck ones. So the other thing that we learned is that someone can be reinfected. Like, we had ASs, they got away with the route, everything was perfect, and suddenly they had stuck routes again. So you cannot really know what is happening. And in this case, we know the ground truth, right? We know when we advertise something, and we know when we stop advertising it. So we can figure out which routes get stuck. But on the real internet, because you never know the ground truth, what it's supposed to look like, it's very difficult to try to guess what is happening. So the final question was, can we do something? And after figuring out that, this affects traffic, after validating with many operators, like we had tier 1s tell us that they face this daily or weekly, and it's actually dropping traffic, we try to figure out if there's something that we can do to fix it. The first thing is an RFC, and it is the send hold timer. And because BGP is so complicated and full of race conditions and all of that, what it does basically is that if you think it's not working for 30 minutes, restart it. So, turn it off and on again, and hopefully it works this time. And it's obviously more sophisticated than that, but that's the core idea behind it. If a session is misbehaving, like you cannot send updates to that, or keep alive like work, but it doesn't actually route, you for 30 minutes, then you reset the session, hopefully it clears, and then it works again. And if every single router on the internet had this today, we think that 30 to 40% of these stuck routes will be gone. But of course, not everyone is going to have it. Currently, no hardware vendor supports it. You can find it in OpenBGP, Bird, and FRR, but no, physical box. So ask support from your vendor. Just point them to this RFC and ask them to add support to their software, and hopefully they do that. And then, when that is added, it has to make it into a stable release, and then you have to upgrade your router. So it's going to take several years for that to happen, and it's again only a third of the routes that will be gone. So it is a long-term solution here. And we want to address, however, as many of these stuck routes as possible, and maybe in the end, solve this problem once and for all. But people have been studying this for 25 years. I'm not holding my breath, but hopefully it will be gone one day. And there is another thing that we are starting, and it is the Stuck Route Observatory. So because there was a lot of interest, and this is a real problem that networks have, the request that I received at RIPE was to keep running this BGP clock. Basically run it forever, or at least for as long as possible, so we can study the effects, the problems that we have better, try to pinpoint specific routers and models and see what the problem is, and then work with vendors or operators to understand what we can do about that. This is going to generate open research data, and we have an offer for someone to create a dashboard where you can see all of the ASs and maybe even get alerts if your AS has stuck routes. It's going to basically run all the time, and then someone else is going to receive BGP feeds, process them, and if there are routes in your AS and you are somehow identified as the person most likely responsible, you're going to get an email, hey, figure it out, like maybe something is wrong. This is again, however, for the synthetic data that we're using. It's not going to solve the real problem. It's just going to help us understand it better. And for that to work, I have the IPv6, of course, because it's great and everyone has unlimited addresses. But if we want to study the old internet as well, we need some IPv4. And I don't have it right now. I don't have multiple /16s sitting around. So we're trying to, we're in the process of trying to find, as much as IPv4 as we can that we're going to use for this purpose. And if you have any and you want to offer it, you can take it back in less than 24 hours if you ever need it. It's just going to help us generate more data and make this problem better understood, at least, from the data we're going to get in the meantime. So it only takes 5 minutes of technical work plus whatever you need to convince your management. So it should not be that difficult. But yeah, if you want to offer any type of space, it doesn't have to be continuous. It could be in pieces. Just come find me, and it's going to help a lot with research into this problem. So that's all I had for today. If you download the slides, these 3 buttons here, they get you to 3 different blog posts where you can read more about this problem and what we've done so far. Thank you.
Thank you, Adonis. Very interesting. Any questions? I have a question myself, if I may start first. So I wonder, do you have any insight about what is the reason for those 3 noisy networks? I mean, obviously, the BGP runs over TCP. The packets are not lost in the transport. It's maybe something on the CPU, on a bug.
Yeah. So the whole thing is caused by, first of all, TCP issues. Like the TCP window is being set to 0, and you can no longer send packets. Like you say to the other side, please send me up to 0 bytes from now on. And then you never tell them to send you bytes again, so this gets stuck. And then other things are, memory corruption, software bugs. Like modern BGP, especially in hardware boxes, is immensely complicated. And there's, a ton of threads there, and it's just very difficult to get it working properly. So these are bugs. However, for this particular ASs, I think it's just, I would guess that it's a problem in the software that they're using. I don't know about the quality of the links that they have. But we had to ignore them because it was just, 10%. So.
No, I understand why you ignore them. I just wondering if you actually contacted these guys to understand understand more. And obviously, the things that you mentioned may cause issues not only for zombies but for other kind of BGP.
Yes. BGP has a ton of bugs. This is just one of them, and we're slowly trying to fix them for everyone, but it's not easy, of course. Yeah. And we try to work with vendors, including Cisco, and we try to work with operators as well. So if you have faced this problem, I'd also be curious to know more about it.
Thank you.
Thank you.
Hello, Kakaru Kaspiros from Console Connect. I would like more to just answer a little bit to Andreas, because I've seen quite a few issues like that. So what usually happens is that the BGP process on a router just stops processing updates. This might be because of memory allocation issues, because you overloaded that router. It might be because of a bug. It might be because some hardware is partly failing. But the interesting part for me is not that. The interesting part is that on typical large-scale networks, you have route reflectors. So what usually happens is route reflectors divide the updates, the peers they need to update, into update groups. And if you have a BGP router that can't process BGP messages anymore into an update group, this means that the route reflector can't send any updates to any of that routers in that update group. So basically, the issue propagates.
Yeah, so if one router within an AS is infected, it can more easily infect other routers there as well, yes. So
exactly.
It's
interesting perspective, thank you. Any other questions or comments?
Yeah, remember the t-shirts and the probes, come find me.
Thank you very much, Adonis.
Of course.